Alright, so we just saw one thing that we can do with mmap, which is to do file I/O. Let me show you another thing that we can do with mmap. I'm going to go ahead and copy our print array here, just as starter code. We're going to create a file called shared1.c. And shared1.c is going to have all of those headers and some others. So I want the pthread header file, some other stuff that I don't know if I'm going to use. In fact, I'm not sure why I'm using a lot of these things. In any case, those are in my notes, so I'm just going to keep them here. Now we're going to write a completely new thing. I don't know that we actually need... we'll keep assert OK, we may not use it. So we can use mmap to map files from disk into locations in memory, but another thing that we can use mmap for is to allocate memory with non-standard flags set in the virtual memory table, in the page table. So here I'm going to say I'm requesting the operating system assign the memory address for the newly mapped memory. I'm going to request one virtual page, or one page, 4096 bytes. I'm going to request that that page be read and write. And then I'm going to request that the flags be map shared and map anonymous. So map shared means that if this page ever becomes shared between two ever becomes mapped into two process address spaces, for example, because we fork, it's not going to be copied. We won't use the copy on write mechanism. It's just going to go ahead and share the physical page between the two processes. Map anonymous means there is no file backing this memory mapping. So we can go ahead and give file descriptor as -1, and offset doesn't matter because there's no file. And we'll go ahead and assert OK on that. Next up, the thing that I want to do is I want to say for int ii0, we're going to fill in the first 10 items of that shared memory as just some data. Then what we're going to do is our favorite thing, we're going to fork. So here we're in the parent. And we're just going to sleep for 1 second. Then we're going to go ahead and mutate the array. So we have this array up here. We filled it in with the numbers 1 through 10. And we're going to change the contents of the array. For every item in the array, for the 10 items that we filled into the array, we're going to replace the sort of 1-digit numbers we had before by hundreds. And then we're going to wait for the child process to terminate. In the child, we're going to start off by printing the contents of the array. Then we're going to sleep for 2 seconds. Then we're going to print the contents of the array. Then in both the parent and the child, we're going to unmap that shared thing just for sort of good style. We're about to exit, so it'll get freed anyway. There we go. There's our test program. assemble it, we find out that we forgot to include a header. We included a bunch of headers that we're definitely not using, but we forgot syswait. Then we forgot to put a semicolon instead of a colon, and now it compiles. So before I run this, go ahead and try to figure out, by staring at this program, let me get the whole main function on screen at once, what is this going to print? Go ahead and pause and think about it and try to figure out what this is going to print. Okay, let's run it. Shared 1. So we filled in the array with the numbers 0 through 9. We did that here, and then we forked. The next thing that happens is in the child process, we're going to print out the array content. So we can see that at that point in time, the contents of the array is as we filled it in here. Then we're going to sleep for 2 seconds. While we're asleep, well, the child is asleep, the parent is going to wake up after its sleep, and it's going to fill in the array with the numbers 0 through 900. Then when the child wakes up 1 second later, it's going to go ahead and print out those numbers as well. We can see that in the child process, the contents of that array are never changed. So we must in fact be sharing memory between the two processes, because if we weren't sharing memory between the two processes, then there would be no way that we would be able to get different results from these two loops. Now, this particular test isn't 100% sort of safe from a sort of C language standards perspective. One of the optimizations that C compilers are generally allowed to do is that if you go ahead and read memory, and then you read memory again without having changed memory, the C compiler doesn't have to compile the code in such a way that we actually go read memory again. It could cheat in any number of ways. In this case, we have an array of 10 items. You could go ahead and load those 10 items into registers, like unroll the loop into like 10 copies of the loop body, go ahead and load all 10 numbers into registers, and then never bother looking in memory again down here. So we wouldn't even see the fact that the other process had done something else, because C does not require that the C standard doesn't require that the C compiler even consider the possibility that there might be a concurrent process running that might mutate memory, like sort of behind its back. Now, in this particular case, probably the sleep system call is special and will tend to make the compiler go look for stuff, but that's not something that we can rely on. That's not specified anywhere that sleep has that property. And so a compiler could come along and in the future decide to just print 1 through 10 again as if there were no shared memory. But here we can see that there really is shared memory, and so this example works. Now I want to do one more quick example here. I'm going to go ahead and copy this to a new file just so that we have everything in the scratch directory. The thing that I'm going to do here is I'm going to take out the sleeps. So if I take out the sleeps, I can still compile it. Alright, what's this one going to print out? Go ahead and pause here, think about it, and then we'll see what happens. Alright, let's see what happens. So now we get the child is going to print the result after mutation twice. We get a nice clean order. The parent ran first, then after the child ran, and so the child never saw the original version of the array before the mutation happens. That kind of makes sense. Let me go ahead and show one more version here. What if I go ahead and instead of mapping like this, what if I take away the map shared flag and replace it with the map private flag? All right, go ahead and guess what this is going to do. We run it, we see what we get is the child sees the original version of the array, and that's true even if we add the sleeps back in. Because with the map private flag set, the page that we're allocating is a copy on write page. So when we fork, the two processes act as if at fork time that page of memory had been copied, and each process, the parent and the child, gets their own copy of it. Okay, so that's how we can do shared memory. And next up, we're going to see how shared memory leads to some problems.